take a moment and go through how to use the Rice strategy to solve an equilibrium problem. Now the Rice strategy, what Rice stands for is reaction, then the initial concentration of the chemicals, the change in concentration, and then the at equilibrium concentrations. The key thing here is trying to arrive at the at equilibrium concentrations, because at equilibrium concentrations is what we use to insert into our equilibrium constant expression. Setting up our equilibrium constant expression for this reaction, which is a ratio of the concentrations of the products divided by the concentration of the reactants, this would be our equilibrium constant expression that we have for this particular equilibrium reaction. The next step in our strategy is we're going to put into place all the initial concentrations of our chemicals. We're given that the CO, H2O, CO2, and H2 all start out initially with a concentration of 1.000 molar. The next piece we're given is it says at equilibrium the H2 concentration is found to be 1.387. We can put that in at the equilibrium concentration for H2, 1.387 molar. What this now allows us to figure out is the size of the change. The H2 had to go up by 0.387 molar to get up to 1.387 molar in concentration. This allows us to figure out the size of the change for each of the chemicals. We can see we have a 1 to 1 to 1 to 1 ratio in our balanced equation. So if the H2 went up by 0.387, the CO2, the other product, also had to go up by 0.387 molar. Whereas each one of our reactants had to go down by 0.387 molar, since this is in a 1 to 1 to 1 to 1 ratio. This allows us to get the equilibrium concentration for all chemicals involved. Now that we have the equilibrium concentrations of all of our chemicals, 0.613 for the CO, 0.613 for the H2O, 1.387 for both the CO2 and the H2, we can insert these into the equilibrium constant expression and calculate our equilibrium constant. Inserting the equilibrium concentrations of each chemical in the equilibrium constant expression allows us to calculate the constant, and it comes out to be about 5.12 is our equilibrium constant for this particular reaction. Let's do a second example of how to use the Rice strategy. The first thing we need to do is write our equilibrium constant expression for this reaction. This would be our equilibrium constant expression for this reaction. It's products over reactants. We have our exponent of 2 here because the balanced equation has a 2 for the HF. Our next step is let's insert the initial concentrations of our reactants into the Rice strategy. We've now placed the given information for our initial concentrations of each of the chemicals involved. All 3 are 2.000 molar. The next step is to identify our equilibrium concentration of one or more chemicals. We're given that the H2 is found to be 0.472 molar at equilibrium. That gives us our at equilibrium value for the H2. This also allows us to find the size of the change, in that to go from 2.0 to 0.472, this had to go down by negative 1.528 molar. Now the reaction, because it's a 1 to 1 to 2 ratio in this balanced equation, if this reactant, the H2, went down by 1.528, the F2 also would go down by 1.528. However, the HF, because it has a coefficient of 2, this would go up by 2 times 1.528 to give us the equilibrium concentration of the HF. 2 times 1.528 is positive 3.056, so our equilibrium concentration of HF is 5.056 molar. We now have our equilibrium concentrations of all 3 chemicals. We need to insert these into the equilibrium constant expression, and that will allow us to calculate the equilibrium constant. This would be our setup where we've placed all the concentrations into the equilibrium constant expression. The HF is 5.056 squared. It's going to be divided by 0.472 times 0.472, and this gives us an equilibrium constant value of roughly 115 for our KEQ for this reaction.